So now we're ready to start the second chapter of the course, which is about a particular numerical measure associated with any square matrix. Determinants have a variety of interesting applications, but I'll start with giving you just the simplest one. They provide a convenient way to determine, in the absence of any other information, if a given square matrix is invertible. And on that note, I want to remind you of a fact about 2x2 matrices. If you have a 2x2 matrix A, and I use the letters A, B, C, and D to represent its entries, we can say that this matrix is invertible if and only if, and the criteria that I'm going to put here is that AD, which is the product of the entries on the main diagonal, minus BC, which is the product of the other two entries, right? So if you form this product and subtract the other diagonal product, you get this expression. Now it turns out that A is invertible if and only if this expression happens to be any number other than 0. So that is actually what's going to motivate the following definition. And the definition is we're going to actually give a name to this expression AD minus BC here, and we're going to call it the determinant. So the determinant of the matrix A is defined by, and the notation we use is DET. So you go DET of A, and that's going to be defined to be the expression AD minus BC. So with that definition in mind now, if I agree to let this be called the determinant of A, well, now I could rephrase this statement and say that a 2x2 matrix A is invertible if and only if its determinant is non-zero. And that allows me to phrase the exact same fact without making up a separate symbol for each of the entries of the matrix. So that's actually really nice to be able to do. Now, that only, of course, applies to 2x2 matrices. We would like to be able to generalize this fact about determinants to higher dimensional matrices, but we can't yet because we don't even know what it means to say the determinant of, say, a 3x3 matrix or the determinant of a 5x5 matrix, because this definition here only applies to 2x2 matrices. So that is why our goal now is to extend this definition to any square matrix. Okay, and this strategy below outlines how we're going to do it. So, well, first, we're going to assume that determinants for the slightly smaller, well, okay, let me back up. So what do we want to do? We want to define the determinant of a general n by n matrix. Okay, and what we're going to do is we're going to start by making the assumption that determinants of the slightly smaller n minus 1 by n minus 1 matrices have already been defined. And then we're going to show how we can use that assumption to introduce a definition for determinants of n by n matrices. Okay, and if we can successfully do that, it's called a recursive definition. And the reason it works is because we already have a definition for 2x2 matrices that we can fall back on. So once we have successfully done this, once we've followed through with the plan that is laid out in this strategy, then what happens is this. 2x2, or determinants of 2x2 matrices are used to define determinants of 3x3 matrices. And then determinants of 3x3 matrices are used to define determinants of 4x4 matrices, and so on up the ladder as far as you want to go. You can just keep on going with it as long as you like. So that will be the payoff in the end once we've done it. But we haven't done it yet, right? I haven't actually shown how we can use the assumption in part 1 to get the conclusion in part 2 here. And that's what our goal is now. So start with an n by n matrix A. And we're also going to add a little bit more. So we're going to say we have an n by n matrix A. And let's say we have two numbers, I and j, which are going to be between 1 and n. Really, this is just saying let I and j be two numbers that are between 1 and n. And really what these are going to be for is exactly what they were for in chapter 1. I is going to be used as an index for the rows of A, and j is going to be an index for the columns of A. Okay, so with that fixed in the background, we can start by defining, well, we can define the minors and the cofactors of this matrix A. And we're going to start with the minors. And there's one minor for every choice of I and j between 1 and n. So that's why we're going to call it the ijth minor. So the ijth minor of the matrix A is defined by this rule here that has a rectangle around it. So the notation we use for the ijth minor is capital M, stands for minor, and then we have two subscripts, I and j. So the ijth minor is the determinant of the n-1 by n-1 matrix obtained by deleting the ith row and the jth column. Well, and remember, we are working under the assumption, remember the assumption we laid out here was that determinants of n-1 by n-1 matrices have already been defined. So if you are willing to accept that assumption, then from that assumption, you get now that this is a sensible definition for the ijth minor of an n by n matrix. Okay, so that's how we're going to do that. So, but really, this is only a definition in the abstract sense because I haven't really told you what that how that determinant is defined. But at least this definition is good, at least as much as you can rely on the assumption that we've laid out up here. Okay, and the other important thing about this is this last part. So if you start with the matrix A, and you have a fixed I between 1 and n, and you have a fixed j between 1 and n. If you delete the ith row, which is what it says down here, and then you delete the jth column, well then you have one less row and you have one less column. And that's why the result is an n-1 by n-1 matrix, the determinant of which is what we define to be this ijth minor. Okay, so that's minors. And I'll give you some examples below, but first I want to introduce one more definition, which is called the ijth cofactor of A. So for each I between 1 and n and j between 1 and n, we have a minor and we also have a cofactor. So the ijth cofactor of A is defined by actually this formula. So the notation, capital C with the two indices I and j, this is the notation for the ijth cofactor. And the way you get the ijth cofactor is you take the ijth minor, which we've written here, at capital M with the ij subscripts, so the ijth minor here, and you multiply it by a power of -1. And the exponent up there is just the sum of the two indices I and j. Okay, so this is a definition that in order to really grasp it, you just have to get your hands dirty and play with it a bit. So that's what we're going to do in the next example here. So here's a 3 by 3 matrix. Okay, so we've got this 3 by 3 matrix A. Let's write down a couple of minors and their corresponding cofactors. So let's start with the minor, or the 1, 3 minor. So I'll write down M1, 3. So that's going to be the ijth minor of A in the case where I is equal to 1 and j is equal to 3. So what we're going to do is we're going to take the determinant of a particular 2 by 2 matrix. So we started with a 3 by 3 matrix, but the 1 and the 3 down here are telling us we're going to delete the first row and we're going to delete the third column, and then take the determinant of the matrix that we obtained from doing that. So what would happen if I delete the first row of A, the 1, 4, 2? That's the first row at the top, right? And the third column is the 2, 1, 5. So if I delete the first row and the third column, really I'd be left with just the 0, 3, and 2, and the 1. So 0, 3, 2, and the 1, and that's what I get, right? So that's the 1, 3 minor of the matrix A is the determinant of this 2 by 2 matrix, which we can work out using this formula up here because it's a 2 by 2 matrix. So we can just go ahead and say, okay, the determinant of this 2 by 2 matrix is going to be 0 times 1 minus 3 times 2. So what does that work out to be? That's 0 minus 6, so you're going to get -6. Okay, so that's the 1, 3 minor of A. What about the 1, 3 cofactor? The 1, 3 cofactor would be C1, 3, which based on this formula, we would just take -1 to the power of 1 plus 3 times the 1, 3 minor. So it's going to be -1 to the power of 1 plus 3 times the 1, 3 minor of A. And the 1, 3 minor of A, we already worked it out, it's -6. So this is going to be -1 to the power of 4 times -6, which -1 to the power of 4 is just +1, so we end up getting -6. So that's the 1, 3 cofactor of this matrix A. Okay, well, let's do a different example. How about the 3, 2 minor and the 3, 2 cofactor? So we'll start by computing the 3, 2 minor of A. So Well, we're going to take the third row now. The first index is the row, the second index is the column. So take the third row and delete it. Take the second column, 4, 3, 1, and delete it. What are you going to have left? Take its determinant. Right, so what will you have left? If I delete the third row and the second column, I'll just have the 1, 0, the 1 and the 0 here, and the 2 and the 1. So I'll have 1, 0, 2, and 1, and then I'll take the determinant. Okay, so see how I got that? Just take the matrix A, delete the third row, and delete the second column. And what you'll have is exactly this. Now take its determinant, and that's how you get the minor. Okay, so let's use the same formula again. So multiply these entries on the main diagonal. You get 1 times 1, and then subtract the product of the other two entries, minus 2 times 0. So you get 1 minus 0, which is just 1. Okay, and that's our 3, 2 minor. What about a 3, 2 cofactor? I better start a little bit more to the left here. I almost ran out of space here. If I want the 3, 2 cofactor, I'm just going to use this formula here, which says just take negative 1 to the power of I plus j. Well, I is 3 and j is 2 here, right? So we've got negative 1 to the power of 3 plus 2 times the 3, 2 minor of a, which this part we just worked out to be positive 1. So really we've got negative 1 to the 5 times positive 1. And of course negative 1 to the 5, that's an odd power of negative 1, so you just get negative 1. So we have negative 1 times positive 1, which is negative 1. And that's the 3, 2 cofactor. Okay, so that's just an idea to give you an idea of how these are actually calculated in practice. But that's the idea of the minor and the cofactor. Okay, and we're going to use those to define determinants.